my previous video, I've established the distribution problem for you. If you haven't watched this, be sure to check it out to follow along. But nevertheless, let's review. You got one source, which needs to send the same data to many receivers. In a unicast-only world, every receiver has its own destination address. 3 instances of the same flow means 1 for each destination address. But what if the audience isn't fixed? One receiver wants to join, another one wants to leave, a third appears somewhere else in the network. Your source shouldn't have to create a new destination identity every time the audience changes. So we need a different abstraction, a different destination addressing mechanism. The question is simple. What should the packet name be? Or more specifically, what should the destination field in the packet identify? Not every receiver, not every list of receivers. Something receivers have in common. The answer is a host group. Your sender sends to the group. Hosts join the group when they want that traffic, and they leave when they don't. The membership could change without changing the ID of that group. That is the fundamental architectural move behind IP multicast addresses. The destination field no longer IDs an individual receiver or a NIC. It identifies a group, and that idea derives what we're about to examine next. But now IP has another problem. A packet still has one single destination field in the header. The network needs to look at that field and know whether it represents an individual destination or a group. IPv4 solves this by reserving a dedicated range for multicast. It's 224.0.0.0/4. Historically, this was named Class D, with the 4 high-order bits being fixed. That leaves 28 bits for the group ID. So the structure looks like this. Those 28 bits aren't identifying a NIC attached to a host somewhere. They are identifying a multicast group. There are 2 other boundaries worth remembering too. 224.0.0.0 itself is never going to be assigned to a group, and the multicast group address won't appear in the IPv4 source address field. The address represents a destination group. Do not forget that. Now comes an interesting question. If those 28 bits ID groups, why not simply allocate addresses sequentially? That is a very good question. But because multicast groups don't all have the same meaning or scope, we need some grouping strategy here. Some exist on the local network, some are used for inter-network control, some are administratively scoped, some use a source-specific model, some have defined allocation mechanisms. So 224/4 isn't one undifferentiated pool. It contains several different allocations and scope regimes. So 224.0.0/24 is the local network control block. Watch out, because those addresses masquerade as multicast, but their behavior more resembles broadcast. 224.0.10/24 is the inter-network control block. There are historical ad hoc blocks. 224.2/16 is associated with SDP and SAP session announcement. 232/8 is source-specific multicast, and 233/8 is GLOP, and 239/8 is administratively scoped multicast. The important point isn't memorizing those blocks, it's understanding why those blocks exist in the first place. There are 2 questions engineers often conflate into one, if you will. Who is allowed to use this address, and how far should traffic using it be meaningful? Those aren't the same question. GLOP, for example, provides an allocation mechanism derived from an autonomous system number. Administratively scoped multicast provides an address space intended for use within an administrative domain. Source-specific multicast changes the identity of the distribution itself. So multicast address planning isn't like find an unused address in 239/8. It's more deciding what the address represents, who controls its allocation, and where that identity is valid. Now let's consider the first multicast address block, the 224.000/24. These are local network control addresses. They are not ordinary app multicast. They are used by network protocols themselves. OSPF and EIGRP are familiar examples. This creates an important operational consequence. A multicast beginner sees multicast traffic and they inspect the IGMP snooping state. So there is no learned receiver. They could conclude that snooping is broken. That conclusion could be wrong, and most often it is. As specified by RFC 4541, packets destined to 224.000/24, other than IGMP itself, are forwarded on all ports. You're entitled to ask why here, of course. The answer is because hosts and routers can use these addresses without first establishing ordinary IGMP membership state. If the network treated them like normal application groups and pruned them aggressively, this could suppress the control traffic required to operate the network. Your OSPF adjacencies will be unpredictable. The forwarding is local to the network. It does not mean the traffic should cross a router into another VLAN, for example. But we are still looking at one layer. The IP packet eventually has to be forwarded across Ethernet. And Ethernet is not concerned with an IP address, as I'm sure you know. It forwards using a MAC address. So the multicast group ID needs another representation. Remember, we had 4 fixed bits. So IPv4 provides 28 variable multicast bits. Ethernet's multicast has 25 fixed bits, the 01005E. Mapping this to IPv4 gives us only 23 bits. You can map and convert v4 to MAC by taking the low order 23 bits of the v4 multicast address and append them into the low order 23 bits of 01005E and so on. But wait. We have a problem. 28 bits enter and 23 bits survive and 5 bits disappear, which means we got 32 different IPv4 multicast addresses that can map to the same multicast MAC address. This is not a bug or anything like that. It is a consequence of the multicast address mapping from IPv4 to MAC. Now, let's examine the problem with an example. Let's take 224.123 and 239.121.129.23. They are clearly different IPv4 multicast addresses, but their multicast Ethernet mapping is the same. Both become 01005E, 010203. That behavior is called aliasing. The IP addresses did not collide, but the Ethernet representation of those addresses did. The problem is introduced by the translation between the two addressing systems. And if you have a problem with that, I suggest you speak to Stephen Deering. Now, this gives us something important to think about between the control plane and the addressing architecture. Switches use a mechanism named IGMP snooping to learn which interfaces are interested in which multicast groups. This is how it manages state. It could use that information to construct the forwarding state or table, but it could not recover bits that were discarded by the IP to Ethernet mapping we just talked about. So if two IPv4 multicast addresses produce the same Ethernet multicast MAC, layer 2 has a shared representation of those addresses. Snooping could reduce unnecessary forwarding and flooding. It could not change the fundamental mapping, so don't conflate the two. Aliasing exists inherently in the addressing architecture because of the size discrepancy. Network switches using snooping forward frames based on the destination MAC address. So if two groups share a single MAC address, traffic intended for Group 1 will be delivered to hosts subscribed to Group 2, even if they didn't want that. So once you understand that mapping, address allocation becomes a design engineering exercise. You don't just need unused addresses, you need an allocation strategy. Some questions you might ask are: how many simultaneous groups will exist? What scopes do they require? Who owns the allocation? Can multiple facilities operate without conflicting? Can the address scheme be summarized, and where? What is the exposure to layer 2 aliasing? GLOP provides us an interesting mechanism that we could think about. It derives the address from an autonomous system number, but GLOP was designed around 16-bit AS numbers. With 32-bit AS numbers, that mechanism no longer provides the same mapping. Don't forget that. There is an alternative noted in RFC 6308. It involves including unicast prefix-based allocation and other allocation mechanisms. What I want you to remember is that multicast addresses need governance at the end of the day. There's another way to manage the address allocation problem: changing what the group means. How does this work? In any source multicast, where the receiver doesn't care which source is sending, the address identifies the distribution group. The source is not part of the group address itself. Source-specific multicast adds the source to the identity. I will cover this in later posts. For IPv4, SSM uses a specific range, 232.0.0/8. The group address only needs to be unique in the context of its source. That changes the coordination problem at hand. Instead of asking who owns this group address globally, the model then becomes: which source and which group am I interested in? That is one reason SSM is such an important part of multicast architecture. It also pushes the burden of source discovery to the application layer. Now, let's move on to IPv6. IPv6 removes broadcast entirely. It also adds anycast. In a v6 world, multicast replaces the function of broadcast, and that changes the importance of it. In IPv4, multicast is one of several mechanisms for reaching multiple NICs. In IPv6, multicast is part of the normal architecture. Neighbor discovery is one example. So IPv6 doesn't simply give multicast a larger address space. It makes multicast fundamental to ordinary v6 operation. Let's have a closer look at v6. IPv6 multicast addresses have a dedicated structure. They begin with FF, then comes 4 flag bits. The high order flag is reserved and must be initialized to 0. If the R bit is set to 1, then the P and T bits must also be set to 1. This indicates there is an embedded rendezvous point address in the multicast address. I will explain what an RP is in later posts. Then comes the 4 scope bits. Then finally, 112-bit group ID. Conceptually, it looks like this, as you see on screen. The scope field is significant. v6 doesn't merely say this is a multicast address. It could encode where that multicast scope is intended to exist. Interface only, link only, admin local, site local, organization local, or global. The same group ID could appear at different scopes. So, for example, you could see FF01 colon 101 and FF02 101 or FF05 101 and so on. The group ID is the same, but their propagation scope is different. IPv6 introduces another useful addressing mechanism. Instead of arbitrarily allocating a multicast address, you could derive multicast addresses from an existing unicast prefix. This is well noted in RFC 3306. As an operator, you likely own the unicast prefix, so that prefix becomes part of the multicast address. The multicast ID is therefore derived from existing addressing authority. This is a different approach from IPv4, and the same framework provides the basis for IPv6 source-specific multicast addressing. Now, let's go back to the problem we discovered in IPv4. 28 variable bits were mapped onto 23 Ethernet bits. That's what gave us the 32-to-1 aliasing space we observed. IPv6 has a vastly larger multicast group ID. The result is a larger number of possible group addresses per equivalent MAC mapping. In practical terms, that makes the IPv4 style aliasing problem negligible. That conclusion depends on the address allocation model, after all. If an organization or an automated assignment system, for example, decides to deliberately pack entirely different global multicast services into identical trailing 32-bit IDs, layer 2 MAC aliasing will reappear. So effectively, the allocation policy determines how much of the theoretical space is actually used. Now, if we put all of this back into a real production network, we might have hundreds of simultaneous multicast groups, or thousands, video, audio, control, telemetry, infrastructure protocols. Address is now doing more than IDing traffic. It is part of the network's operation model. So the engineering questions then become, which multicast block are we using? Or what does that block mean? Who or what allocates these addresses? And what is the intended scope? Is the allocation deterministic? Could different groups alias at layer 2? Are local network control addresses being treated correctly? Are we actually using any source multicast, where source-specific multicast would be more appropriate? And can the addressing scheme survive another facility being added? There are 5 things that I want you to take away from this video. Number 1, a multicast IPv4 address identifies a host group, not an individual NIC. Number 2, the IPv4 multicast address space contains different allocations and scope blocks. Number 3, the IPv4 to Ethernet mapping discards 5 bits of group ID, making layer 2 aliasing a structural problem. Number 4, IGMP snooping can manage forwarding states in a switch, but it cannot change or help you with the underlying address mapping. Number 5, IPv6 makes multicast fundamental to the architecture and the v6 network operation. It incorporates scope into the multicast address and provides a dramatically larger group ID space. Let's recap what we covered today. A multicast address is not simply an IP address with a different first octet set. It exists because the network needed a way to name something different, not an individual receiver, a group instead. Once you drill that into a mental model, the rest of the architecture follows easier as you navigate multicast. IPv4 reserves an address range so the destination field can identify that group. The range is divided and categorized because groups have different allocation and scope requirements. The group ID has to cross into Ethernet. That translation preserves only 23 of IPv4's 28 variable bits. 5 bits are lost, and that's where aliasing comes from. IPv6 changes the architecture again. Broadcast is gone. Multicast becomes mandatory, fundamental, and an operational requirement. Scope becomes part of the address, and the group ID space becomes vastly larger. So don't look at a multicast address and ask only, is this a valid address? A better question is to ask, what group does it represent? Who controls its allocation? And what scope does it have? And what multicast model does it represent? And what happens to that ID when the packet crosses into layer 2? That was my multicast addressing architecture video. Thanks for watching.